Oh, good afternoon. Welcome to this second session of our spring webinars organized by Emconsoil. And without much more ado, we will immediately start with the two presentations we have today. And the first presentation will be from Tectero BV, Wouter de Weert, with PFAS destruction in water with non-thermal plasma, and then William Leys from AECOM Belgium will follow with another electrochemical oxidation destruction methods. Both have half an hour where we handle the questions immediately after the presentations. So to start with, we have Wouter. And Wouter de Weert is the owner of Tectero BV. Tectero develops, engineers, and manufactures non-thermal plasma technologies for the conversion of liquids and gases. Okay, Wouter, the floor is yours.
Okay, good afternoon. My name is Wouter de Weert. I represent Tectero during this presentation. And first of all, of course, I would like to thank the organizers to give me the opportunity to talk about PFAS destruction using non-thermal plasma. I would like first to introduce our company and activities, and then I would like to talk about plasma and non-thermal plasma conversion in liquids and gases in general. Further, I'd like to highlight a couple of engineering application aspects. And then more specifically, of course, I would like to talk about the use of non-thermal plasma for the destruction of PFAS in water, the related destruction mechanisms, applications and results, and finally compare this with other existing technologies. So Tectero is a privately owned SME established in 2013 and based in Ghent, Belgium. We are an ISO 9001 certified company since 2021. And our general goal is to provide chemical and environmental process solutions using non-thermal plasma technology. And we want to offer this in a flexible and cost-effective manner. The main activities of Tectero are the development of non-thermal plasma technology for the conversion of liquids and gases, but we also carry out contract research and development for third parties in the field of green chemistry, renewable energy, and environment. Well, to come directly to the plasma subject as such, solid, liquid, and gaseous matter are commonly known fundamental states of matter. But less known is that plasma is actually the fourth fundamental state of matter, and it's often referred to as a moderately or entirely ionized gas, and is characterized by the presence of significant amounts of charged particles and contains a lot of free neutrons, electrons, radicals, ions, and atoms at an increased energy level. And in terms of temperature and electron density, plasma systems can be characterized in two main types or groups. On the one hand, you have the thermal plasmas, and on the other hand, the non-thermal plasmas. And thermal plasmas are characterized by electron, ion, and gas temperatures, which are above 10,000 degrees Celsius, and electron densities of at least 10 to the 20th electrons per cubic meter. And non-thermal plasmas, however, exist at much lower ion and gas temperatures, while the electron temperatures remain high. And at Tectero, we only work with non-thermal plasmas at the moment. And in our current portfolio, we carry out conversions of organic liquids. These are mainly plant oils that we convert into chemical intermediates, which can replace mineral oil-based counterparts. And since 3 years, we work on the destruction of persistent organic pollutants in water using this technique as well, which is now the main topic, of course, of this talk. We also use non-thermal plasma systems to convert gases such as carbon dioxide, methane, syngas, and not surprisingly, also fluorinated gases as well. And we apply different conversions, such as elimination, hydrogenations, polymerization, substitution, additions, and reverse water shift reactions. And the use of non-thermal plasma is already a very common industrially used application in terms of related to material engineering. But we focus and explore mainly the fields of chemistry and environment, but also application in medicine, agronomy, and even in space are possible. And yeah, one of the big advantages of plasma reactors is that they can be switched off and on in seconds, and therefore we strongly believe that non-thermal plasma technology has many possibilities into the current grid evolutions, where electricity will be available in on different moments and variable pricing, and we can modify and adapt to that availability and pricing with non-thermal plasma systems. Also, if this electricity is generated by solar, wind, and hydrogen, this is fully sustainable. And at Tectero, we have an in-house capacity to engineer and manufacture our own mechanical parts and reactor systems. And on top of that, we develop and produce our own power electronics, such as IGBT controllers, needed to power these reactor systems. Now, as everybody in this audience may know, PFAS substances are synthetic compounds with unique properties, including high chemical and thermal stability, which are very persistent in the environment. And since the 40s, PFAS have been used in numerous consumer products and industrial applications. And such applications, as everybody knows, are firefighting foams, paints, coatings, textiles, paper, pesticides, etc. And yeah, PFAS is an omnipresent collection of molecules, which is, yeah, depending on the sources, is about 4,000 to 12,000 different compounds. And the carbon-fluorine bond in PFAS is thermodynamically very robust and provides persistence, inertness, and stability to the perfluorinated molecule. And three main fluorine characteristics contribute to that. There is the high electronegativity of fluorine, tends to attract shared electrons and contributes to a strong carbon-fluorine bond, and results in low reactivity and a high thermal stability. And on top of that, there is the polarity of the bond, which contributes to the strong acidity and low pKa values. And further, the fluorine is very difficult to polarize, and the electron density is not easily impacted, which contributes to the typical specific surface properties of PFAS. Yeah, and finally, the fluorine and the carbon bond is of the carbon fluorine bond is very small, and it shields off the carbon, and it contributes again to the chemical stability and the low reactivity. And this all together contributes to a very high bond dissociation energy of about 450 kilojoules per mole. And we, by using non-thermal plasma, provide highly reactive species with energies high enough to overcome this and to actually break down the carbon-fluorine bond. A non-thermal plasma reactor is in essence built up by two electrodes, a dielectric barrier, a plasma gas, and a power source. And the main consumable is electricity. So if the electricity is generated by a renewable source, the system is completely sustainable. And the plasma itself, as told, generates many different radicals and reactive species and highly energized electrons and photons, sufficient to break down the carbon-fluorine bond. In this slide, I would like to explain the commonly proposed destruction mechanisms, which are studied by many different groups and people. So the plasma-generated reactive species attack the sulfonated functional group on the PFAS molecule and create a very unstable polyfluoroalkyl radicals. And these radicals again react with hydroxyl radicals, converting them into polyfluoroalcohols, which are also quite unstable and further transform to PFOA in this case, by splitting off the fluorine. And the same mechanism is then applicable for the PFOA, where then the chemical attack is on the carboxylic functional group. And then the same process occurs and repeats itself. So in this slide, I can show basically the stepwise breakdown of the PFAS molecules, where the process is repeated while the chain length is reduced from a C8 to a C7 to a C6 and so forth. Additionally, it is also suspected that there is an immediate split off of fluorine that occurs in this breakdown process. It must be said as well that a non-thermal plasma is a non-selective process. So this means that any other organic substance will be attacked by these reactive species and is also broken down into its elemental components. The final end result of such degradation process is eventually fluorine ions and carbon dioxide, which is released. In terms of applications and targeted results, first of all, the process itself, and that's what we focus on, is a continuous flow process. So we don't work in a batch process as such, and we aim to go to a full destruction and mineralization of the PFAS molecules. Currently, we target for most of our clients the 100 nanogram limit, while we look into the 20 nanogram limit as well, because that's potentially the limit for the near future. And we are able to degrade different types of water, such as drinking and groundwater, with relatively low loads, speaking of hundreds of nanograms per liter to a couple of micrograms per liter. To these limits, also we can treat process water with very high loads, up to 80 micrograms per liter, and also leached water, which has a combined high load and, for example, a high salt content, which can be problematic for other techniques, which we can also degrade to the required limits. Also, emergency response water from, for example, firefighting incidents can be treated. And we have no, let's say, pre-treatment required except for a sand filtration in order to remove suspended solids and particles from the water. And our process can be integrated in existing water treatment plants as a first bulk remover or as a final polishing step, or can be used as a standalone application. So when we compare with other existing techniques, we have proven that we can remove PFOA and PFOS with very high percentages, up to 99.9% removal efficiencies. And I think we outcompete active carbon and ion exchange methods in this. We have no chain length limitation, contrary to active carbon and ion exchange. We can basically, if we increase the residence time of PFAS molecules in our reactor, we can destroy any chain length present. There is no residual waste in our process, and I think that's contrary to active carbon of other or ion exchange methods, where there is always a residual waste which requires further treatment or disposal. Our methods is versatile because we are able to adapt to variable concentration levels in the influent water. There is a very low sensitivity to ions. We have tested that in many different ways. And this is also, I think, an advantage towards active carbon or to ion exchange resins for sure. We have no sensitivity to organic loads. On the contrary, extra organic load will also be destroyed and reduced. We have done many tests on different wastewaters and waters which contain a general COD level, and we can reduce the COD levels with 40 to 60%. We have no sensitivity to pH, which might be a problem for active carbon and ion exchange. And our CO2 emissions are very low, and for sure very low when electricity used is generated or is sourced by a renewable energy source. CO2 emissions with the use of active carbon or ion exchange will always be higher because there is potentially an incineration required to destroy the residual waste or to recover the active carbon. And in terms of cost, if we put our relative overall cost per cubic meter at X, we believe that we are 20 to 30% cheaper than active carbon and 40 to 60% cheaper than ion exchange resins. I think as a summary, I think we can say that we have a full destruction potential of individual perfluorinated compounds in water using plasma technology, and there is no residual waste stream created. We have a fully sustainable process if renewable electricity is used. We have a very effective removal method with inlet concentrations up to 80 micrograms per liter tested, and we achieve 100 nanograms per liter output concentrations. We have no harmful residuals present. We have low maintenance requirements. We destroy other persistent organics as well at the same time as well, and we reduce the COD levels. We can provide pilot tests on, let's say, drum or IBC scale, and we are now in the process of constructing 2 containerized units which can then be deployed to certain sites, or we can design and engineer for fixed plants with capacities up to 40 cubic meters an hour at this moment. So that leaves me to thank you for your attention and leave my contact details for anyone who has any further questions.
Okay, thank you, Wouter, for this nice presentation, and also nice that you kept really in time. So there's certainly the possibility for some questions. You can also ask those questions in the chat, but now you also, yes, there's already the first question that appears. Can you work batch-wise?
That's possible. We can work batch-wise, of course. That we have to modify a system with an influent buffer tank and maybe an effluent buffer tank, and then that way we can work batch-wise.
Okay, there's also some hands that popped up. The first is Christophe Bogaert. You can ask your question.
Yes, good afternoon, everybody. Thank you very much, Wouter, for the presentation. I'm Christophe. I work for the NUO, the Belgian sector federation of the waste and recycling sector. Mm-hmm. I think we already met during the BBT studies. I had a small question. I don't know if you already have experience with it, but I know there are some issues with the so-called precursors of not yet PFAS compounds who can become PFAS compounds. Do you already have with your system an experience there where it appears to happen, and do you have a view on if they are present, are they also fully reduced or destroyed?
Yes, we are aware of this this potential problem, and what we do is when we ask for analysis, we do not only ask for analysis for 10 or 20 compounds, but we have analyzed for 40 or even 60 compounds in some cases, and we check if we actually polymerize the compounds, but that is not the case. We actually see that for many of the teleomers, which are also present in many of the analysis and which are not on the list yet, that we actually destroy them as well. So we are actually sure that we don't have any polymerization reactions. And on the downside, for let's say the lower carbon chain lengths, we have also carried out different checks on this and analysis, and we do not find any residual products which are produced in that respect. Of course, this is continuous improvement. We carry out GCMS scans on effluents that we create, and we check continuously if we produce any residual compounds. But so far we haven't detected those. And I know that in literature this often appears, but I think the reason is that in literature many people do research and work in batch processes. So this means that they actually run the same water for many minutes or even hours in the same batch, and then of course you might be create compounds that you not desire. So that might be a reason why we don't have it, and other people in literature have it a lot. I think that's due to the batch or flow mode process.
Okay, thank you very much. I'm gonna take the opportunity because I saw all the other hands. Perhaps I missed it, but in terms of cubic meter per hours, what is your handling rate with the system?
Well, of course, we are now in full development and deployment for larger systems, but our reactor capacity in terms of cubic meters per hour is surface related, of course. So as soon as we increase the surface area, we can handle bigger flow rates. So that this is just a matter of multiplication or additional reactors. And in terms of an existing reactor, which is, for example, capable of handling 10 micrograms per liter at 1 cubic meter an hour, the same reactor will be able to handle 10 cubic meters at 1 microgram per liter. So this is obviously related to the load or the incoming load of the water.
Yeah. Okay. Thank you very much, Wouter.
Yeah.
Thank you. Because the second hand has disappeared, I go back to the chat where there's a question from Ruth Saiz. How many full-scale remediations have you already carried out?
So far, we have not carried out remediations ourselves. It's also not our purpose to act as a remediation contractor. It is rather our purpose to either sell or hire out our equipment and machinery.
There's another follow-up question from Anna Litek. And what is the energy consumption? Is it dependent on the concentration? That's the question.
Yeah, it's for sure dependent on the concentration levels. At very low concentration levels, like for if you talk about a couple of hundreds of nanograms per liter, we talk about maybe 1 or 2 or 3 kilowatts an hour per cubic meter. If you go to higher concentration levels in the tens of micrograms per liter, you would obviously have more energy consumption, which is then in the range of 10 to 25 kilowatts an hour per cubic meter. In that magnitude of order, of course, other parameters which also influence, like what is the incoming COD load, what is the conductivity level of the water, etc. So these are obviously also parameters which influence the consumption.
Okay, next question is coming from Guillaume van de Kerkhoven. Am I correct if I say that currently you can individually filter until 100 nanograms per liter, in the future until 20 nanograms per liter? What with the proposal of EPA, which proposed levels to 4 nanograms per liter for drinking water, then of course?
Yeah, I think we have not tested that yet, but I think as such the system should be able to handle it. I think we just have to increase the residence time in the reactor, of course, and of course we have to see how you can measure that, because the measurement of such low concentration levels is also an issue, I think.
Other question is coming from Niels Koyen. Is it correct to state that the small carbon length PFAS molecules will take less time to destroy with non-thermal plasma than longer ones, or is this dependent of the functional groups?
Well, in terms of functional groups, the sulfonated versions, they tend to be destroyed very, very quickly. The carboxylic ones is a bit slower. And in terms of chain length, it is the higher the chain length, the easier it degrades, because it's related to the solubility, of course, and the lower the chain length, the more difficult it gets.
Okay, thank you. Are there other questions? I don't see any hands that have been raised until now, or other questions in the chats. Wouter will stay until the end of this webinar, so if other questions would pop up, you can certainly ask them after the presentation from William. No other questions? No, not really. Then we can go to the second part of this webinar, where we have a presentation from William Les, who is Senior Environmental Engineer and PFAS Lead Europe at AECOM Belgium. And this method of DE-FLUORO was developed by AECOM in collaboration with their partners. Is a first economically and environmentally sustainable treatment technology for the destruction of PFAS from contaminated liquids without generating hazardous waste. We're really curious, we're interested, William, in your presentation. So the floor is yours.
Yeah, thanks, Johan, for the introduction and for the Emconsoil platform and the opportunity to present the fluoro. So yeah, William Les from AECOM Belgium, as Johan pointed out, PFAS Lead Europe, and also responsible for the fluoro deployment, let's say, within Europe. So I'll give you a very high-level overview, giving the time constraints, let's say, about the fluoro, what the technology is, and what the constraints are, or where you can apply it, let's say. So the fluoro PFAS destruction technique, and as such, it is a electrochemical oxidation. Now, electrochemical oxidation, as such, is not such a well-known technique. It's not that special, let's say, but here specifically for the fluoro, for PFAS, special electrodes and the way of handling it has been studied very into much detail, and that's what you see here at the bottom of the slide, the development pathway, let's say, for the fluoro. We already started, or AECOM already started way back in 2015-16 with the first literature study, let's say, what might be viable techniques to destroy PFAS. As with the plasma technology, it's very important to understand that also the fluoro is a destruction technique. It's not a separation technique. It's a destruction technique. And we now also see that destruction techniques are really the way to go for these forever chemicals, let's say. So way back in 2015-16, it was in stage 1, the proof of concept literature. It was like electrochemical oxidation is the way to go. First test, let's say. And then we went to more feasibility study, bench scale tests, not only on spiked materials, but also on real world samples, real groundwater samples, real highly loaded PFAS water samples, let's say, to see if it already worked on a lab scale with real world samples. Then went to slightly bigger reactors in lab scale, let's say. And then since 2020 to 2021, the first big pilot demonstration test was implemented in Australia, and that's the picture you see here. I'll show you some results of that first pilot test, the things that we have learned, things that we have, the challenges we have encountered, let's say, and what we did to overcome some of those challenges. Stage 5, scale up commercialization, going to very big full scale the fluoro techniques will be the next stage. So just the fluoro, electrochemical oxidation, the fluoro in the PFAS market. This is from an article very recent November of last year from GWI, where you see that there was a nice overview, American US focused market, let's say, nice overview of the emerging PFAS destruction techniques. And there you see from the emerging techniques to the most mature techniques. Now, this really does not mean that emerging techniques are not good. They're just under development, let's say. It only states that electrochemical oxidation is a known technique that's already been developed when it comes to PFAS in a more mature way. You see that there are very open about it, very quite a lot of companies looking into the electrochemical oxidation, but in the article it was also clearly stated that AECOM is leading the electrochemical oxidation technique at this stage on a global scale. Already to show you that we have outrun solely the lab testing, let's say. So as I just mentioned, we have completed a first rather big pilot test in Australia, where we tested a wash water solution, and several big pilot tests are ongoing. For instance, we started in 2022 with a flow-through system demonstration for DE-FLUORO in the US. I can talk a little bit about it as well. Another batch system is ongoing in Australia right now, and I will already take some lessons learned from those ongoing trials, and certainly give you some insights in the results of the first pilot test that was performed in 2021 in Australia. Next to that, we still continue to do our bench and lab tests, let's say, as a first test to see if a certain waste stream is suited for DE-FLUORO. Now on that, I can already state that we have a very small test set here in Europe as well, in Italy, which we hope to be able to perform these lab bench evaluation tests by Q3 in 2023. Now on the pilot test that has been performed in Australia, so there it was for a confidential governmental organization. So there we treated a 53 cubic meters of a combination of AFFF, so firefighting foams, and also a decontamination solution. So pretty high loads on PFAS there. So the question there came from the client to test it in the framework of their AFFF tank decontamination project for their foam transition program. So, and the objective there was treat first flush, first spent, let's say AFFF concentrate to a level that was suitable for discharge to their own on-site treatment system. So here you see the pictures of the fluoro. So electrochemical oxidation occurs in a single reactor, which you can see here. Here you have like 6 reactors in this container. You also see that it's pretty flexible. We can scale it, let's say, we can put in more reactors if wanted. Here we have 3 reactors, both in parallel. We can put them all in series. We can put everything in parallel if we want. So this is then the setup, the configuration of the current or the pilot test in 2021 at that stage. So electrochemical oxidation, it is in a 20-foot container that can be shipped and transported on site to site. There's also a possibility to put it on a centralized site, let's say, and bring PFAS loaded waste or water to the DE-FLUORO, so it's pretty flexible on that side. So at this stage, it was treated as a standalone technique, so solely DE-FLUORO that treated the spent AFFF or the first flush of AFFF. Also very important, and what we are working on, and certainly in the new systems, is that there's quite a lot of telemetry systems being applied so that it can be handled and operated from a distance, but also by just a single operator, let's say, that you can leave it in the field. And of course, you always have to go and check periodically, let's say, but it is pretty, it can be operated by a single operator. Now, pilot results from 2021, and I do want to stress it, these were the first results back in 2021. We have obtained additional results, but instead of just showing you the last and best results, I wanted to show you the results that we obtained, the data that we obtained in 2021, the lessons that we learned, let's say, and where we didn't manage to come to a complete destruction, and what we did to overcome that, let's say. Now, what we see here is 4 trials, 4 experiments. The first 3 were first flush, so water that has been flushed through a container that contained AFFF, so high load on PFAS there. And what we did was we played, let's say, with the current, with the residence time, with the flow rate, with the amount of cycles that we had to. So there we saw that in the first experiment. So what we did was we did not solely analyze for PFAS or PFOA. We also did TOF analysis to show and see if we got a complete destruction, yes or no. Also for the PFAS compounds that we are not looking for at the moment, let's say, and the precursors as well. I haven't got a slide with all the details, but we have for one test cycle, let's say, there we tested for at least for 5 to 6 moments in time, let's say. Also, we tested not only for target PFAS, TOF analysis, but also for other constituents that could be present, COD and all those kinds of stuff. So pretty elaborate analytical suite that we applied there. We also checked for emissions, if there were any emissions, let's say. Also within the reactor vessel, if the PFAS didn't stick to the reactor, let's say, because then we wouldn't be treating PFAS, but then we would just be absorbing the PFAS to the reactor. So to make sure that that didn't happen, so that we could close the mass balance and to be sure about the destruction. And it's not that we are losing PFAS somewhere in the system that we're not taking into account. So by playing with the amps, with the voltage, with cycling, and so for this specific first flush water, we managed to come to a destruction of TOF. So let's say total PFAS as such of 96.4% for PFAS, and before also 95 or more percent, let's say. So at that stage, that was more than enough to meet the criteria at that stage to go there to their own water treatment plant, let's say. We could go lower if we wanted, the same as with the plasma technology that Wouter just explained, if we would have increased the residence time or the cycles, let's say. Now, what I also wanted to mention during that first experiment where we really treated AFFF concentrate as such, it was not a success at that stage. Now we managed to overcome that, let's say. We had some additional foam management because, of course, when you treat AFFF, foams can be formed, of course. We had some additional foam management, and we managed to come at that stage in a limited cycle time, let's say, to a breakdown of more than 90%. So at this stage, one of our best tests, let's say, on AFFF, we have like 3 green boxes that are being ticked, let's say. So in overall, based on those first experiments, and also based on later and ongoing tests, let's say, we see that a significant PFAS mass reduction can be obtained within the first 8 to 24 hours. That's what you see here, that the most reduction will be obtained in those 24 hours, let's say. And at that stage, the concentrations were low enough to comply with the thresholds at that stage to go to the water treatment plant, or to go to a secondary polishing. Now, if we wanted to treat longer, let's say, and that's always the balance between costs and how far do we want to go, we could meet really like almost complete destruction, 99% plus, let's say. At that stage, we had recirculation rates between 2 to 6 cubic meters per 24 hours. And as I mentioned, with the telemetry and working on that, improving that as well, the system can be operated in 24/7 with minimal supervision, let's say. The energy consumption at this stage was between 3.3 to 5 kilowatt hours per day. And the same as with the plasma technology, since it's based on electricity, there is this potential to operate on solar power, supplemented with a battery. So yeah, also sustainable in that way. There's also the remote location capability. Not so interesting, let's say, within Benelux, but for instance, in Australia or maybe in other parts of the world where you have to drive like a couple of hours to go to a certain area, it might be very, very interesting as well. So based on those first pilot tests, rather big pilot tests, let's say, and the follow-up and ongoing tests, we see that that we obtain pretty good, very good results when it comes to DE-FLUORO as a destruction technique. Now, as I mentioned, I think, I did mention these tests were performed on AFFF, first flush AFFF. Back in 2016-17, when we treated real-world samples, let's say, it was already pretty clear to us that electrochemical oxidation or DE-FLUORO technique as such, it is not valuable, or we are not going to apply it to treat, let's say, for a pump and treat, to treat groundwater with a couple of 100 nanograms per liter. It's really for very high concentrations, low volumes, let's say. So there you are, like for AFFF concentrate spent, PFAS impacted wash water, but also like when you have like a first step, like an ion exchange resin, where you have still bottom waste that you can treat, reverse osmosis brines, maybe from a landfill leachate or directly from landfill leachates, let's say, and any other separate and concentrated waste stream. So it's depicted here below. You have a PFAS containing waste stream, pre-filtration if required. And then you have the DE-FLUORO. You see that there is an air emission control system, just to be sure that even there you're not having the air emission PFAS being limited to air. Can be durable, sustainable because of the solar panels, battery storage. Is an electrical system. So then if required, or just based on your waste stream or highly loaded PFAS stream, depending on the objectives that you want to meet and the evaluation between putting in a lot of energy and a longer residence time, let's say, there might be an optimum of polishing the effluent of the DE-FLUORO, or just keep on putting energy into to obtain the very low objectives that we all are aware of, let's say. So it can be just as a polishing step, activated carbon, but it can also be that you put in another step, for instance, like ion exchange, where you do a recirculation. Another test, and maybe I didn't point it out specifically, is in the US. We are currently testing DE-FLUORO also as a coupling technique after, for instance, what we call the SAFLA, like foam fractionation, where you pump up groundwater, you have the foam fractionation, and then there you have a low volume, highly concentrated PFAS stream, let's say, that can be treated with DE-FLUORO. That's a test that's ongoing as we speak. So in short, DE-FLUORO's performance as commercial application, so it's as a standalone on-site system, as a closed loop on-site treatment train, and combination of the above, let's say. So to summarize, so pilot 1 demonstrates that DE-FLUORO is a viable destruction technology. It can avoid off-site disposal, and it's deployable in the field both as flexible on-site or as fixed facilities, let's say, and can be coupled, and that's also very important, not only as a standalone, but also as a coupling technique for polishing or creating a closed loop treatment train, let's say. And also applicable for foam transition programs, let's say. So, and low energy consumption, and you can reach your supporting your ESG commitments when you use, for instance, solar power. That's it really in a nutshell, high level. I can go into much more detail from a technical point of view, but I don't think we have the time here. If there are any further questions from a technical point of view, I'm more than happy to welcome to answer them, or you can get in contact later, let's say, no problem. You have my email address here, and if there are any other opportunities to further discuss, yeah, more than welcome. Any opportunities within Europe, let's say, I will look further into that together with and that's very important, together with the global team. If there are any global opportunities, let's say, I will transfer them to our global technological DE-FLUORO experts. So that was it in a nutshell. And if there are any questions, I will try to answer them or give you some feedback afterwards. So go ahead.
Okay, thank you, William, for this interesting presentation. Also nice you kept on in time so that we have room for different questions. And some questions already appeared in the chat. And the first is about the energy consumption. So it will be easier if you read it with me, but I'll just for everyone, I'll go to the question now. So 2 to 6 cubic meters per day and 3 to 5.5 kilowatts per day comes to a power range of 2.75 kilowatts per cubic meter to 0.5 kilowatts per cubic meter. Is that correct?
I'm very bad at calculating by head, let's say, from my head. I had it on another slide, and I think it is could be in that range. I can come back to that, let's say. Bear in mind, these were the results of the first pilot test that I presented. We have been improving and are improving, let's say. Yeah.
Yeah, that's a question from Lars van Bassel. So for if there is a further need for clarification, you can certainly contact Lars van Bassel. Then a second question is coming from Christel Tarchalski. Thank you for the presentation. Which levels, concentrations did you achieve during the pilot tests? Yeah. And what do you expect you may achieve in the future, given that the regulatory values are decreasing?
Yeah, I think in this case, it was really like for PFAS, that were the targets, let's say. We could manage, certainly when you put it in like 100 hours, let's say, to go to non-detect, if you wanted, let's say, certainly between lower than the 100 or the 20 nanograms per liter. It was also important to mention that we do the TOF analysis, so we take everything into account, let's say, so that we can also future-proof, let's say, that we are destroying not only PFAS before, but also the precursors and any other PFAS compounds that we're not looking for at this stage, let's say. So we can go to a complete destruction if we want, but there again, as I try to explain, is there must be an optimum as well between what it will cost and what to reach, let's say. So it could be that you will say we will obtain that low threshold value, then go to another waste treatment plant, let's say, or that you just say, well, it's worth the extra effort, the extra energy, and go as low as you can to non-detect at this stage.
Okay. Are there other questions? It's also possible if you want to raise your hand or otherwise in the chat.
I can also state that quite a lot of the questions that were formulated during Wouter's presentation, I think the same answer that Wouter formulated, let's say, do apply also for electrochemical oxidation when it comes to will short chains be attacked? Yes, they will, but it will take more effort compared to the longer chains and so on. So, yeah.
The next question that appeared in the meantime, that's from Niels Koyen.
Yeah.
What are typical byproducts produced by your technique?
We have checked for perchlorate, for instance, in certain, because sometimes, of course, you have water which contains other constituents. What we have seen, and opposed to in literature, let's say, where it's stated that you will have a lot of potentially quite a lot of byproducts with electrochemical oxidation. In the test that we have performed there, we saw that the perchlorate concentrations, let's say, remained pretty stable and did not really increase at that stage. Of course, same as with plasma technology, at the end you will have CO2 and HF or fluoride ions, let's say.
Yeah, another question is coming from Jani Ulay. Thank you for the presentation. What kind of electrodes do you use for PFAS destruction, since the electrodes for such kind of reactions need to be very stable, for example, like boron-doped diamond electrodes?
Completely correct. And I can only state we use very, very good electrodes. So I cannot disclose the electrodes. Yeah.
But I understand they are very good. Yeah.
Absolutely.
Okay.
Yeah.
In the meantime, no other questions. I have one question myself, and it's coming from the summary where you say, and it's a slide that still appears on the screen for the moment. It can be coupled with other PFAS separation treatments. What would be the interest for someone to couple it with other PFAS separation treatments, and can give an example of this?
For instance, like foam fractionation is also a separation technique. There you still have the PFAS waste, and then you still have to go to incinerate it, let's say. We all already know that, for instance, the American defense, like DoD, doesn't want anything to be incinerated anymore. So as soon as incineration is out of the loop, let's say, then you still have this PFAS waste that can be treated with DE-FLUORO on the site as well. The same with landfills where you have the leachate. Sometimes those landfills are already equipped with reverse osmosis or with an ion exchange. So there again, you are having a rather small volume, high concentrations, and then you couple the fluoro to treat it on the spot, on site, let's say. There will be not a standalone, but a coupling technology.
Okay. Are there the last possibility, if you still have questions for William, or perhaps also a question that came into your mind for Wouter, then there's the last possibility.
Or afterwards, still possibilities.
Or afterwards, yes.
Yeah.
I think you have from both presenters with their expertise, they are available for you. So if you want to ask questions, I think they are certainly open to it to answer your questions. So make use of this possibility. If there are no other questions, then I would like to close this session, and I will not do it before I just give you already some view on the next session that will be on next Thursday, 23rd of March. And we will handle two specific new emerging contaminants. That's about microplastics contamination and also pesticide residues across European ecosystems. So you're welcome for the next session on the next Thursday. And then I want to thank, first of all, the presenters of today for their clear presentations, also for answering the questions, the interaction we had with you as a public, and also for the public for following this session of the Emconsoil webinars.